Hello, everyone, and welcome to the session on unbiased recommendation and evaluation. I'm Pablo Castells, speaking from Madrid, and I will be the chairing the session. So we have four long papers, followed by one reproducibility paper, and finally industry talk. As you know, remember that you can ask questions on the Huba agenda entry for each presentation. You can upvote questions, and we will read them for presenters to answer. I encourage you to follow up with speakers and continue the discussion after the session on Huba. So without further ado, we're going to start with our first presentation. The speaker is Yoshifumi Seki from Gunosy. He's going to talk about building and releasing datasets from commercial systems. So the floor is yours.
Okay, can you hear me? Okay.
Yeah.
Okay. Hello everyone. My name is Yoshifumi Seki, senior researcher in Gunosy. Today, I talk about our paper, a method to anonymize business metric to publish implicit feedback dataset. First, I talk about the background of this study. Dataset publication is important for recommendation system studies. Datasets, however, contribute to develop recommended systems such as movie rents and Netflix price. However, implicit feedback datasets from commercial service are not enough. Recommendation systems have adopted in many and various services, so many and various datasets are needed. Sorry. Our motivation was to make it easier for commercial service to publish datasets. There are some business risks to publish dataset. RIKEN confidential business metrics is the most crucial risk. Thus, before publishing a dataset, researcher must get approval by a business manager. Many business managers are not specialists in machine learning or recommendation systems, so the researchers should be responsible for explaining the risk and benefits. In this study, we focus on an implicit feedback dataset. Implicit feedback datasets include confidential business information and users' personal information. We have four contributions in this paper. First, we summarize the challenges of building and publishing datasets from commercial service. Second, we formulate the problem of building and publishing a dataset as an optimization problem that seeks the sample rate of users. Third, we applied our method to build datasets from the raw data. The raw data has more than 1 million users with 100 million interactions. Lastly, the implementation of our proposal method and the dataset built by our proposal method are public. We have achieved to persuade our business manager using this method. Thus, I talk about tasks in this paper. We only focus on following three data: user behavior logs, user attribute, and article category. Our task is publish subsets of the user behavior logs, and we do not publish user attributes and article categories. This is the reason as user privacy and content rights. We build datasets by sampling user approach. To explain this approach, we show the example that users' behavior log include these three users' history. If users' behavior logs are sampled directly, the consumption history of users are missing. To keep the consumption history of users, we sampled users and collect log associated with sampled users. Okay, we pose the following three challenges to publish a dataset. First challenge is to anonymize the business metrics. We don't want to disclose confidential business metrics. If the users are sampled uniformly, some business metric could be easily estimated. We must sample the users with a non-uniform distribution. Second challenge is to maintain fairness. Recently, fairness is an important topic in machine learning. Publishing unfair dataset indirectly contributes to creating unfair machine learning models. We assume that publishing a fair dataset is very important for company reputation. Third challenge is to reduce popularity bias. If the dataset is built by uniform sampling item and popular category are less frequently less frequently sampled. We believe popularity bias is a problem in building dataset, and the publisher must keep a certain amount of interactions with unpopular category items. Thus, I talk about our proposal method. We formulate our task as a problem of finding the sampling weight of users. We want to anonymize our business metrics. However, formulating this challenge is impossible because it needs to enumerate all the metrics that we should anonymize. In other words, we sample users to make the distribution of datasets closer to specific distributions. This figure shows our method. We sampled users according to sampling weight to close target distribution. We solve optimization problem. Under this assumption, our loss function is defined here. This loss function calculates the distance between expected click distribution and target distribution using Weierstein distance. We also show two loss functions of second and third challenges. Each expected distribution is simply calculated using sampling weight. We find the sampling weight at which all the loss functions have small values. To achieve this goal, we minimize the sum of these loss functions. Okay, as an experiment, we built a dataset from the raw data in our news delivery service. The number of users in the raw data was more than 1 million, and the number of clicks in the raw data was more than 100 million. From this raw data, we built datasets that consisted of the behavior log from 60,000 users. We built 8 datasets from user behavior logs. For anonymizing business metrics, we adopt two-time target click distributions, DPF1 and DPF2, and users attribute and category click distribution are controlled or uncontrolled. These distributions are controlled as uniformly. The dataset statistics shown in this table. DPF2 datasets are more sparse datasets than DPF1. Category controlled datasets are more sparse than uncontrolled. Thus, dataset properties are changed by sampling strategy. These figures show the cumulative densities of number of clicks on datasets. This result shows that we successfully controlled the click distribution of the dataset, and hence this business metric can be anonymized. The distribution of both user attribute and category are also controlled successfully. Next, we confirm how the evaluation of our 8 datasets differed. This table shows the result of algorithm comparison. The result shows that DPF1 and DPF2 have different trend. Especially, evaluations of DPF1 dataset were similar to uniform. Item 2 back is best and item KNN is second. The dataset and the DPF2 had a different result. GR4 work achieved the best performance except both the attribute and category are constrained, whereas item canon achieves the best if both are constrained. This may be because the dataset of DPF were very sparse. These results suggest the performance of algorithm differed in how the dataset were built. In this study, we do not imply which parameter is better or worse. It is necessary to select a sampling setting according to the purpose, and it may be important to publish dataset with various settings. Finally, I conclude our study and talk about the limitation and future works. Implicit dataset commercial service are important to recommended system studies. However, publishing a dataset is difficult due to some business risks. Contrary to this importance, this difficulty has not been discussed and the solutions have not been proposed. In this study, we summarize 3 challenges and propose methods to solve the challenges. This study is first attempt to reduce the business risk in publishing a dataset. Limitation and future work is following. One limitation is we did not give a theoretical guarantee if the impossible and just estimation. Other limitation is this study only considering the user item interactions. There are many challenges in the risk. However, previously, researchers have not discouraged researchers have not to discuss how to build a dataset and has not shared the knowledge with the community. We hope that our work will lead more discussion and propose building and publishing dataset, and that many datasets will be published. Thank you for listening to our presentation. Please visit our project page and use our implementation dataset. Thank you.
Okay, thank you very much, Yoshifumi. Thank you for sticking to the allocated time as well. So we have some questions from the audience. I will read them and so you can answer. So first question is there an intuition behind using NDCG and hit rate metrics to evaluate the performance of recommender system algorithms on published versus original data? If so, do you go for end-to-end optimization?
Yeah, it's difficult problem. So the first question is very heavy. Of course, original algorithm performance was important. In this paper, we share the uniformly sampled data set that it's mainly that is similar to original performance. So depth sampling is also we consider that depth performance is also important because this algorithms sample the unpopular category items more frequently. So this data set contribute this set is contribute minor category long tailed item or popular versus popularity bias. So I don't think the needs to end-to-end optimization of original data. We build data sets. So we build data sets. The settings by the setting to their research purpose. Is it okay?
Yeah, I think so. So there's another question. It's how do you solve the anonymization of location data, such as the coordinates?
So how? Oh, sorry. Sorry. How? Pardon. How?
Oh, yeah. So how do you solve the anonymization of location data, like coordinates?
How solve the publishing? Update animation, the location data. So it's more difficult. So and I think so. Location data is more personal data. So it's suffered from the de-anonymization is more terrible. So but so sequential data. So the sequential data is important. Location anonymization. So, but so it is similar to our data, our problem because the location. So popularity. So publishing data set easily estimate popular location from public data. So some sampling strategy can achieve that location data anonymization. Sorry, so I don't care about this problem, but it's very important. These discussion and studies more needed, I think.
Okay. So finally, I will take the freedom to ask a question myself. It's a curiosity. I checked your paper and I found that you, with hit rate, popularity gets worse results than random. Is that right? And if that's the case, so this is something that I personally have experienced in some very specific experiments. And what does that? I mean, why is that, and why could that reflect?
Why? So why? Pardon. Why?
Yeah, why? I mean, why could it be that popularity gets worse results than random?
Yeah. So this case, so in you see that especially deepest sampling, it says so in this case, so we sampled in the category sampling, we sampled unpopular categories more frequently. So popular category items not sampled frequently. So popularity estimation is not affect. So affect is affect the uniformed one. It has it suffered from the popularity bias, and so random methods achieved more performance. We think.
Thank you. I think it's a very interesting finding. Okay, so we will should move on to the next speaker. So thank you, Yoshifumi. You can let's virtually upload the speaker and move on to the next one. So our next speaker is Yuta Saito from is Masahiro Sato from Fuji Xerox from Japan, and he's going to talk about methods for unbiased learning for recommendation. So you can start anytime.
Hi, thank you for the introduction. I'm Masahiro Sato from Fuji Xerox. It's my pleasure to talk about unbiased learning for the causal effect of recommendation. Wait a moment. So this is the outline of my talk. First, I will introduce what is the causal effect of recommendation and why it's important. Then I describe our unbiased estimator and unbiased learning. And next, I'll show experimental results and summarize my talk. So from a perspective of service provider, a goal of recommender is to increase users' purchases or clicks. This results in an improvement of sales and user engagement that are important measure of business success. In a common setting of recommender systems, a user receives a list of recommendations and might purchase some items. If the recommended items are purchased, it is typically considered successful recommendation. However, is this true success? Now think about counterfactual scenario. What would have happened if these items were not recommended? Some items could have been purchased even without recommendation. So by considering both factual and counterfactual outcomes, now we can know whether each recommendation increases sales or not. So from this reasoning, we think this is a true successful recommender. To formulate our problem setting, let's introduce the concept of causal effect. This is defined as a difference between the purchases if recommended and purchases if not recommended. Now we can reinterpret the goal of recommender. To increase users' purchases or clicks, we need to rank items by the causal effect. So the ideal ranking from the previous examples should look like this. However, there are two challenges in this new ranking problem. First one is unobservable nature of the causal effect. To calculate the causal effect tau, we need both YT and YC, but actually only one of them can be observed for specific user item pair. So that means we need to estimate the causal effect. But there's a second challenge, the bias by confounding. Typically, both recommendation and potential outcomes depend on user and item characteristics. For example, popular items are often purchased and might often recommended. So under such a confounding, it is difficult to distinguish the causal effect and user's natural behavior. So this results in a bias in the estimate of causal effect. In this work, we define the ranking metrics for the causal effect of recommendations. We propose an IPS-based unbiased estimator of the metrics, and we developed our unbiased learning method based on the estimator. In the field of recommender system and information retrieval, previous work on unbiased learning addresses the selection bias. They essentially predict either YT or YC, but not targeting the causal effect. Another line of work is a recommendation for the causal effect. They are not addressing the bias by confounding. Okay. First, I'll introduce a general ranking metric. It is expressed as a weighted average of positive feedback. Here, this rate is determined by the ranking position of items, and the ranking position is determined by the predicted score. This expression covers several popular metrics like AUC, precision, and DCG. Here, this average rank is a metric used in a pioneering work of unbiased learning. We redefine this ranking metric by substituting the YUI with tau UI. So this makes a causal effect version of general ranking metrics. We first construct an unbiased estimator of causal effect, as expressed here. This ZUI is the indicator of recommendation, and PUI is probability of recommendation, also called propensity. This rating method is called IPS, and it essentially upweights the rare events with low probability. With this estimate, we can create an IPS-based estimator of the general ranking metrics in the causal effect versions. However, the IPS methods are known to suffer from high variance. So we remedied this problem by restricting the denominator. So this is called propensity capping. So after deriving our unbiased estimator metric, then we derive the learning method. Since the estimator is not differentiable, we derived here the differentiable upper bound for the causal average rank. These terms, underlined terms, are used for SGD to achieve the differentiable. So this is the differential upper bound, and we use this term for SGD. So let's go to an experiment part. We conducted experiments on semi-synthetic datasets. We have two settings of propensity. One is original to the data distribution. The other is personalized and heavily skewed. But I have to mention that this personalized setting has some mistake. So I have just updated experiments on archive. It was posted yesterday, so it will appear soon. Okay, so now I'll explain the data original experiment. We conducted 5 experiments, and now we show 2 of them. Okay, so this is the result of category level performance comparison. Each learning methods are used for matrix factorization model. And here DLC is a proposed method, and BLC is a biased one. And this is the product level that has the larger number of items. Here again, we can see the DLC mostly outperforms other baselines. Our methods however, requires a propensity, which is a probability of recommendation. If it's not available, we have to estimate it. So we investigate how robust the misspecification of the propensity. Here we can see for the wide range of misspecification, our method outperforms other baselines. So as a summary, we propose an IPS-based unbiased estimator for the causal effect version of the ranking metric, and we developed an unbiased learning methods that are applicable to a wide class of recommender model. For future work, learning methods for other metrics can be developed, and the enhancement of unbiased estimator is possible, for example, by using W reversed. So that's all. Thank you for your attention.
Thank you very much, Masahiro. So we have a question from the audience. I'm going to read it for you. And the question is, how does this work relate to the navigational use of recommenders? Sorry. That is, recommendations that would otherwise be reached through a search engine, but are more easy through a recommender panel.
Okay, I think the navigation recommendation should predict the user's behavior beforehand and suggest some item user would purchase next. I think in this way, maybe users' time to find some item could be shortened, but our objective is not that. We want to find some serendipitous item which users would have not purchased even without if there's no recommendation. So okay, so that's the difference.
Okay. Another question is, why do you need synthetic data in the dataset?
Because as mentioned, the causal effect cannot be observed. So that means there's no ground truth. So I think this is a difficulty in this kind of research.
Mm-hmm. Okay. Then how does one decide on what to cap the propensity at when you use capping?
What to cap?
So I guess this means so if you do capping in propensity, how do you set the capping? The threshold.
This is a kind of hyperparameter, so we tuned it by validation.
Okay. Okay. And more questions. Can this idea be extended where instead of an item, embeddings are predicted or constructed for the user?
I think in general, our method can train any model. So instead of conventional matrix factorization, maybe we can create a FISM or any other deep learning model or anything can be trained. So am I answering correctly?
Mm-hmm. Yeah, so it's not specific to doing embeddings for items. It could also be applied to user embeddings, right?
Yeah, actually, we create the user and the item embedding because we train the matrix conventional with traditional matrix factorization with user and item embedding.
Mm-hmm.
But what I mean is the other model can be also trained with this.
All right. And one last question. Can I use your method to quantify the need of recommendation? That's a tricky one.
Yeah, if that means the need of recommendation is whether there's some room to improve sales. I think our estimator can use it to estimate whether there's further room to improve sales or not. So, okay, if this answer is not correct, maybe we can discuss later because it's difficult.
Sure. I mean, there are more questions, so I think you can follow up on the Q&A after the session. So thanks again, Masahiro. Thank you. And we are moving on to the next presentation that is going to be delivered by Yuta Saito from Tokyo University of Technology. It's work that focuses on post-click conversion. Please, you can start.
Yes, can you hear me and see my screen?
Yeah, all is fine.
Okay, great. Let me now start now. Okay. Hello, everyone. My name is Yuta Saito, an undergrad student at Tokyo Institute of Technology, Tokyo Tech. And today I'm going to talk about my paper, the robust estimator for ranking matrix with post-click convergence. So in this work, I studied the offline evaluation of ranking performance of recommenders using two-stage click conversion, two stages of feedback system, often observed in the e-commerce recommender interface. So let me now use an Amazon recommender interface as an illustrative example. So here is a hypothetical user searching for a statistical machine learning textbook. And he or she now clicks the ESL, the element of statistical learning book. I think it's famous worldwide, but the click itself is not the outcome here. So what we want to maximize, what we want to optimize is the expected number of conversion in the future recommendation opportunity. So we observe the conversion indicator in the second stage user behavior, right? Only for the item with a click. Here is the ESL book, right? So the important point here is that we cannot observe conversion indicator for the other item in the same recommendation list because they are not clicked by the user. Right, so suppose you are the data scientist or in the recommendation interface, and you may want to recommend item with a high conversion rate, CVR, to maximize revenue from users or to maximize the expected number of conversions itself. So here is an example, a hypothetical example of a top-3 recommendation interface. There are two recommenders, recommender A, recommender B, and you see from the table that the recommender A is better than recommender B. It's simply because recommender A can now create a recommendation list having more conversion compared to the other recommender B. So what we want to do in the offline evaluation is to identify which recommender will obtain as many conversions as possible using only available information in the offline environment. But there is a challenging difficulty in this kind of offline evaluation. We cannot use a conversion indicator for user item pair without a click. What we can use in the offline evaluation is a conversion indicator for user item pair with a click, right? So there are many missing conversions in the offline evaluation. So we have to do some kind of statistical inference, statistical estimation to do the accurate offline evaluation of a ranking performance of recommenders in the offline environment, right? So this is the motivation. And let me now define the ground truth ranking performance of recommenders. So here is a ground truth ranking performance, which is now defined as the weighted expected number of conversions in the future recommendation opportunity. So this is now defined by using the true conversion rate, PCBL, for all user item pairs, which is unfortunately unobserved to the analyst in reality. And C is a ranking function or the weighting function, we can say. So ranking function can be, for example, average relevance position, discounted cumulative gain, or you can use any other such as a recall function or the precision function, right, to define the ground truth ranking measure. But what is important here is that it is desirable or it is ideal to calculate the ground truth ranking measure directly to identify the best recommender among many candidates. But unfortunately, calculating the ground truth ranking measure directly is impossible because there are some challenging difficulties in evaluating recommenders in an offline environment, including the missing conversion and the selection bias issue. The first challenge is a missing conversion. So please remember, so in the previous Amazon recommendation example, a user first clicks the item or the item web page, and then they decide whether they should, buy the item or not. So in this situation, when a click does not happen at the first stage, then the conversion indicator, the true outcome here, is not observed to the analyst at the second stage, right? So, meaning that this means that we cannot use conversion indicator for user item pair without a click as a first stage, as depicted in this kind of illustrative figure. So this is the missing conversion problem. And we also see that conversion indicators are often highly sparse in general recommender applications. So we have to address the sparsity of conversions in the offline evaluation as well as the offline learning phase. And the other challenge is a selection bias issue. So again, we can use only conversion indicators with a click in the offline evaluation. And observed conversion data is often biased by many sources of bias, such as presentation bias, position bias. There is also popularity bias, was a bias by pass recommender system, pass recommender policy. So I think many of you remember that yesterday's amazing keynote on bias and recommender system or bias and interactive system. So we have to do the same thing in the offline evaluation. We have to, for example, address the kind of a distributional sift between clicked events and unclicked event to do the accurate statistical inference of the recommender performance on the whole population or whole user item pairs. So this is the selection bias issue. So in summary, what we want to do in the offline evaluation is to estimate the ground truth ranking performance, which is now defined by using ground true conversion rate for all user item pairs. So we want to construct an accurate estimator for the ground truth using only accessible information in an offline environment. And what is accessible is a set of conversion indicators here denoted as Y, UI, which is a binary random variable. But we can use conversion indicator for user item pair with a click. And ZUI is another binary random variable representing whether the item I is clicked by user U or not. Okay, so this is the source of offline evaluation. So a previous famous popular solution for the ranking performance estimation is to use the IPS estimator, the inverse propensity score estimator, originally proposed in causal inference literature. So the previous RecSys 2018 paper proposed to use this IPS to estimate the ground truth ranking performance using only biased implicit feedback. But this kind of IPS estimator can be easily extended to our two-stage click conversion, two-stage user feedback setting. So this is the definition of IPS, and the basic idea behind IPS is to weight observed conversion by the inverse of the CTL, P-CTL here. And the CTL is the probability of an item I being clicked by user U in the ROC data. And by doing this inverse CTL weighting, we can easily show that the IPS estimator is unbiased for the ground truth ranking measure, which what we want to estimate here. So it's fantastic. But the problem here is that the variance can be huge, which is a notorious weakness of the IPS estimator in a general literature. And especially when conversion indicators are highly sparse, which is a general phenomena, general situation in the recommendation application, right? So the variance issue might be problematic in the recommender system application. So the main motivation in our paper is to alleviate the variance issue of the previous unbiased IPS estimator in the ranking performance evaluation. So for this purpose, we propose the W-Bust estimator for the ranking performance of recommenders using two-stage user feedback for the first time in the literature. And this is the definition of our proposed estimator. And you may think that the definition is a bit more complex, a bit more difficult than the previous IPS. But the basic idea behind the W-Bust is fairly simple. It uses the estimated CVL, p-hat CVL, to impute the missing conversion information for user item pair without a click, right? So remember that the IPS estimator does not use any information of the missing conversion, which is the source of high variance. So to solve the high variance issue, our W-Bust estimator uses the estimated CVL to impute the missing conversion information. And by doing this, the W-Bust estimator uses information about all user item pair in the offline evaluation phase, right? So, and thanks to this technique, imputation techniques, the W-Bust estimator is, first of all, unbiased for the ground truth ranking measure. The expectation is equal to our estimate. So this is the same property with as the previous IPS. And the fascinating feature with the W-Bust estimator is that the variance, it has lower variance than the IPS estimator in most cases. So this is a remarkable theoretical result because the W-Bust estimator enables us to accurately or more efficiently estimate the ground truth ranking performance of recommenders, or the ability of recommenders to obtain as many conversions as possible, even if conversion indicators are often high sparse, which is often occurred in recommender system, right? So this is our main contribution, main theoretical methodological result. Let's use W-Bust to estimate the ranking performance of recommenders when you have click conversion like a two-stage user feedback. Okay, finally, let me now present briefly experimental result in our real-world experiment. Due to the time constraint, I have only 10 minutes. But the important takeaway message is that the W-Bust estimator outperforms the other baseline estimators in the offline evaluation task. I compare the W robust estimator to the two baseline, including the naive estimator, which is a biased estimator, and the IPS estimator is an unbiased, but it has high variance. So the W robust estimator, W robust estimator enabled us to accurately estimate ranking performance of a candidate recommenders. And by doing this, we can do the accurate model selection or accurate model evaluation without the online experiment. Okay, so in conclusion, we studied the offline evaluation of the ranking performance of recommenders using possibly biased, possibly sparse click conversion like a two-stage user feedback. And the previous unbiased estimator, the IPS estimator, has a large variance, especially when conversion indicators are highly sparse. So we propose the W-robust alternative to estimate the ground truth more and more efficiently. And the proposed estimator evaluates the performance of arbitrary many candidate recommenders accurately in our real-world experiment. That's it. Thank you for listening. And please refer to our paper if you're interested in details, including theoretical analysis, interest in semi-statistic result, and the discussion on the related work. And yeah, thank you. And I'm now happy to take some questions.
Thank you very much, Yuta. So there's a number of questions. So one question is, would it make sense to use something like browse time instead of, as a conversion indicator, instead of click or along click? Would that make sense?
Oh, I cannot find the.
Or maybe let me rephrase if I understood the question. So what you do is you want to predict after a click whether there is a conversion. That's your target for prediction. Is that right?
Oh, okay. So I think it's a question about the W robust, right? And so is it the question about the W robust, right?
So, yeah, I guess so. Yeah,
yes. Okay, so to use the W robust, you are right. We need an estimation of the CBL behind of the evaluation. So we can do this by using only observable information using like a logistic matrix factorization method. And actually, I discussed the way to estimate the CBL beforehand of the evaluation or beforehand of using W robust in our paper. So if you're interested in detail or if you're interested in the whole procedure of a W robust estimator, please refer to our paper. I think we discussed that point in section 4.
Mm-hmm. Okay, thanks. Another question is someone is asking for the source code for the experiments on the W robust estimator. I'm not sure if that's on the GitHub repository already, so seems like people are asking for it.
Yes, I will. I have prepared a brochure, but I think I haven't pushed it yet, but I will do it in a day, I think. Yeah.
Okay, so that's a promise. Okay, one more question. If I want to implement this in a real-world system, do I need to log anything beyond the probabilities needed for IPS?
Okay, thank you for the great question. The answer is no. So we can do the W robust estimation using information same as the IPS estimator. So the implementing our W robust estimator is remarkably simple. So it's one of the benefits of using W robust, I think. Yeah, but thank you for the great question.
Okay. And well, I will ask one last question myself. So in your experiments, you evaluate your metric by error on metric value, if I understood properly, compared to unbiased evaluation. Is that correct? So you measure the error between the ground truth metric value and your unbiased metric value. Is that right?
Yeah, exactly. I compare the ground truth, the divergence between the ground truth and the estimated value. Because
so would it make
no,
sorry. Yeah. So would it make sense to compare the ranking of systems rather than the metric values? So that according to your metric, some system is the best, then the second, third, and then according to the ground truth metric, you have another system ranking, and then you could compare them with like Kendall correlation. Would that make sense? I mean, it's a very technical, specific question.
Yeah, that's a very.
Did you try that?
Yeah, it's a very good question, I think. So you mean that we should, for example, focus on the model selection, right? Or system selection, right?
Exactly.
It's I think the future work, interesting future work. And actually you're right. I now focus on the model evaluation, meaning that I want to minimize the missed error in the offline evaluation. But one possible future work in practice is that we can focus on the model selection program.
Exactly, because in the end you want to know what's the best system. Maybe you don't care if the metric value is twice as high than the other, but just that it's higher. So it's the comparison and the qualitative outcome.
So we may be better when we focus on the model selection. But
all right, excellent.
Discussion.
Okay, thanks, Yuta. So thank you again for your great presentation and great work. And let's move on to our next speaker. And this is Bowen Yuan from the National University of Taiwan, who's going to present their work on unbiased position-aware click-through rate prediction. So please start anytime. You can, turn on your camera. Okay, good.
Okay, sorry. Can you hear me?
Yep.
Okay. Okay. Hello, everyone. I'm Yuan Bowen from National Taiwan University. Today, I will present our latest work on biased ad click prediction for precision-aware advertising systems. This work was done in collaboration with Yaxu, Xia, Zhenhua, and Professor Lin Zhiren. In this work, we focus on the ad systems. In a typical scenario of ad systems, we assume we have n ads and k precisions. And for each request, an ad system retrieves k ads and place them to the k precisions. We give a simple example as follows. We already have 5 ads and 3 precisions. So we retrieve the 3 ads and place them to the 3 precisions, and some of them are clicked by users. So the goal of the ad system is to maximize the revenue from clicks on parsed display ads. And in this work, we consider the precision-aware scenario where an ad placing various positions has different click probabilities. So to maximize the revenue for each request, the system displays the k events with maximize the sum of the expected revenue computed by the bid of this ad, which is the price paid by advertiser if the ad is clicked by users, and times the click probability. And because this click probability is precision dependent, so we call it precision or CTR. And this problem is a standard assignment problem. So choosing the k events from the p and k permutations costly when n is large. So to have an efficient display algorithm, we assume for any events, its precisional CTR can be expressed as non-precisional CTR p tilde ij times a same probability beta k. With this assumption, the optimal k events can be efficiently chosen as follows. We first retrieve the top k ads according to the non-precisional CTR times the bid. Then we place the retrieval k ads from the first precision to the kth precision, where we number the precisions according to their beta values. Now we need to estimate the non-precisional CTR. However, for most systems, as we do not know if an ad is seen or not, so the observations from the non-precisional CTR and the same probability cannot be collected. So we have no training labels for estimating the non-precisional CTR. Instead, we have training labels for estimating the precisional CTR because we have the precision-dependent click information on past displayed events. So the core problem is how to estimate the non-precisional CTR from the precision-dependent labels. To accomplish this, the existing approach first learn a precisional model, G, from the click information on parsed display events to as the estimation of the precisional CTR. And we extract a non-precisional model, F, to give the prediction of the non-precisional CTR, just as the following example show. However, in this work, we argue the non-precisional model F obtained in this way may be heavily biased. Record that the existing approach first to learn a precisional model G on parsed display events. We point out that learned the precisional model G's and bars only if the following display distribution is uniform, and which indicate that the parsed display events were uniformly chosen. However, as we mentioned, a practical system tends to display events with a higher expected revenue. So the selection bias occurs in learn the precisional model G, and the non-precisional model F extracted from this bias model G is also biased. Additionally, suppose we have addressed the issue of the selection bias, and now we have an unbiased precision model. We call it G-star model. And from this G-star model, we expected to extract the unbiased non-precisional model. We call it F-star model. And we expect this F-star model can give unbiased estimation of the non-precisional CTR. However, the extracted model can be shifted by an arbitrary constant D as follows. Clearly, the top KS retrieval by this shifted model times the bit are not same as those by the ground truth model times the bit. To address these issues, we propose our solution. We start from addressing the selection bias caused by the non-uniform display. And the simple way to do so is to collect the training set by uniformly displaying events. However, it causes significant loss of revenue. And so our idea here is to consider non-display event to simulate a scenario where all events can be displayed so that the selection bias can be addressed. For position-aware system, the non-display events include the events of non-retrieval add. Recall the examples add 3 and add 4 were not retrieved. So their events colored by blue belong to the first type of search events. And the second are events of retrieved add with non-placed precisions. In this example, the add 1 was retrieved, but it's only placed to the precision 2, while the precision 1 and precision 3 are the events of search of the retrieval adds with non-placed precisions. So by considering all events, the click information can form a dense binary tensor as follows. And with this tensor, we propose to directly learn the non-precisional model F by solving the following fully labeled problem. And we prove the resulting model give unbiased estimation of a precision-independent CTR, which equals to alpha times the non-precisional CTR. And because the alpha is a constant for all events, the top KS retrieved by the precision-independent CTR times the bit are the same as those chosen by the non-precisional CTR times the bit. However, for non-display events, their labels are unsolvable. We have no training labels for such events, so we apply counterfactual learning techniques. We first collect a small but unbiased subset through the uniformly displaying, and we then learn a model A from the unbiased set to use this model impute labels for any non-displayed events. And next, by following a doubly robust method, we solve the following unbiased problem, where for the display event, their loss terms are weighted by the propensity score. And for non-display events, we use the impute labels to compute their loss functions. Okay. And next, I will present our experiments. For each dataset, we generate a training set as follows. We first do the display event generation by the following 3 versions. The first one is biased one, and the events are non-uniform displayed according to their expected revenue. The second one is unbiased one. We directly collect the events by the uniformly displaying. And the third one is absolute gradient. It's a combination of a small ratio of unbiased data set and the large ratio of the biased set. And for label generation, we generate the precision-dependent click and all clicks as labels for display events. Besides above settings, we also consider ideal setting where the events are unbiased ones, and we generate precision-independent clicks and all clicks as labels for ideal setting. And for the test set, we apply the ideal setting on different time window. And we compare the following approaches. The first one is gradient. This is the existing approach which learns the precisional model G from the the bias data set, and we extract the non-precisional model from it to give the final predictions. And the second one is random. It directly learns a model from the large unbiased training set. And third one is CF. It's a learned model by the counterfactual learning framework, where we use a small ratio unbiased data set to train an imputation model to give imputed labels for non-display events, and we solve the problem based on the W robust. And the last one is ideal. It's learned a model from ideal setting. Its performance is considered as an upper boundary result. And experimental results are as follows. We can say the Grady performs the worst. And due to the selection bias, as we mentioned, the learned precisional model G is biased, and the extracted non-precisional model F is also biased and give poor predictions. And let's see, ideal and random, they perform the best. And the good performance of ideal is reasonable because it directly learns from the precision independent labels. However, for random, we can say by addressing the selection bias, the non-precisional model learned from precision-dependent labels still can give unbiased estimation of precision-independent CDRs. And finally, let's see the CF. By considering non-display events, CF performs significantly better than Grady. In contrast to random, CF only needs a very small ratio data for the uniformly display, so it's practically useful. Let me conclude this work. In this work, we first argue the non-precisional model F obtained by the existing approach gives a bias estimation of the non-precisional CTR, because we point out the issue of selection bias, and we show that even if a learned precisional model G is biased, the extracted non-precisional models can still be biased. And next, we derive a novel counterfactual learning framework to directly learn the non-precisional model, and we prove the resulting model can give unbiased estimation of the precision-independent CTR, and the top K as chosen by the precision-independent CTR time to beat is same as expected ones by the non-precisional CTR time to beat. Okay, that's all. Thank you.
Thank you very much, Yuan. So we have time for some questions. So the first question is about keywords. So would it be possible to model keywords of interest when creating ads and optimizing clicks into your model?
Sorry, I lose my connection. Okay.
Oh.
So you are okay. Now I can hear. So your question is
the question is So how do you model, or would it be possible to model keywords in your model?
Keywords or interest with creating an ad and clicks on. I'm not sure this question is so related to my work, but I guess the question's answer maybe the model keywords or the interest kind of features. Of course, if we want to model CTR predictions or tasks, we can add the keywords or interest in or the input features. I'm not sure if this is the right answer to this question. I'm not so got the question's point. Sorry.
No problem. Okay. I have another question from myself. So how about the feedback loop? Like, so I guess using your model, you decide to play some ads on some higher position, I guess, right?
Yeah.
So then in the next iteration, they will get more clicks. And the next time you update your model, maybe a feedback loop bias could be introduced. I mean, does the question make sense? And if it does, would that be handled by your model, or something else would be needed? Like it would need to be extended with something to deal with the feedback loop.
Okay. So if I understand correctly, you means whether the feedback loop can handle search bias problems from the precisions, or is this question?
Yeah, it's like I mean, if you use a predictions to make decisions, like this ad is very likely to get clicks, so I'm going to place it higher.
Okay.
But then there's a reinforcement of your assumption. So it's going to get a gets richer effect because of that. And I wonder if that can be handled directly in your model, or maybe it's a different problem that needs a new solution, a different solution.
Okay. So the feedback loop is kind of the way to reduce bias of some parser displayed events, but we can say in a new loop we still display the events according to their expected revenue, and a new model trained from this loop generating data still can have a bias. So the only way is that we should address bias in each loop clearly. The feedback loop cannot fully address the selection bias problems. Yeah.
Okay, thanks for the answer. And sorry that there are more questions and we cannot take them right now, but I encourage you, Yuan, and the audience, the people who are asking, to follow up on Q&A on Huawei later. So thank you again. And then, so we're moving to the next presentation. This is a reproducibility paper, and it's going to be presented by Zhu Sun from Macquarie University in Sydney, Australia.
Hello. Hello, Pablo. Can you hear me?
Yes, loud and clear.
Yeah, thanks for your introduction. Yeah, my name is Zhu Sun, and currently I'm a lecturer at Macquarie University, Australia. Today I'm very glad to present our research paper, Evaluating Rigorously, Benchmarking Recommendation for Reproducible Evaluation and Fair Comparison. And I will go through the following 5 parts. So recent decades have witnessed the great prosperity of recommender systems in both academia and the industry, and they have been widely studied and applied in various domains, such as the e-commerce, the location-based social networks, and the multimedia, and so on. So with tremendous amount of the recommendation algorithms being proposed, one critical issue has attracted much attention. There are no effective benchmarks for evaluation. This consequently leads to 2 major concerns: unreproducible evaluation and unfair comparison. Different from other domains like computer vision, where mature benchmarks are available for evaluation, while benchmarking recommendation is challenging in 2 aspects. First of all, we have a lot of data sets from different platforms. So for example, in the movie domain, we have movie lines, Netflix and Amazon, and even for the same data sets, we may have various versions. For example, we have movie lines 100K, 1 million, 10 million, etc. Besides, different papers may adopt different data processing strategies, different data splitting method, evaluation metrics, and parameter settings, and so on. And most importantly, majority of the papers do not report details on data processing and parameter settings, which leads to inconsistent results in reproduction by different researchers. So these issues motivate us to investigate the evaluation rigorousness in recommendation. As a starting point, we focus on top-end recommendation task, which is one of the most important tasks in recommendation. And to this end, we systematically review 185 papers for implicit feedback-based top-end recommendation, which were published in the recent 3 years on 8 top-tier conferences. And we summarize essential factors related to evaluation, such as the utilized data set, the data processing strategies, the parameter tuning strategies, and so on. And through a holistic empirical study, we comprehensively analyze the influence of different factors on the final recommendation performance. And based on the results, we create benchmarks by proposing the standardized procedures for evaluation. And we also provide the performance of the state-of-the-art. Besides, we also release a Python toolkit, RIKEN, for rigorous evaluation. In summary, our work shines lights on the urgent issues of rigorousness in the evaluation for recommendation and lays foundations for future investigation. And now let's talk about the paper collections. As we mentioned, we review papers published in the recent 3 years on 8 top-tier conferences. At the starting point, we focus on the method for implicit feedback-based top-end recommendation. To this end, we search the accepted full paper list for the 8 conference in the recent 3 years, and we consider papers with titles containing the keywords recommend or collaborative filtering. Finally, we manually select papers that adopt ranking metrics, such as precision recall, to evaluate the performance for the recommendation. So the figure shows the distribution of the paper collection. And based on the paper collection, we perform the analysis. So first, we analyze the utilized data set. Overall, there are 16.5 different data sets utilized in the 18.5 papers. So we conduct a careful selection to choose 6 data sets by considering their popularity, their domain diversity, authority, and information richness of the data sources. So the figure here shows the top 15 widely used data sets in the paper collection, and our adopted data sets are highlighted in red. Regarding data preprocessing, we find that around 15% of the paper adopt the preprocessing strategies, and among them, more than 16% of them use 5 or 10 filter settings, and others adopt other settings. So besides the original settings, we further consider 5 and 10 filter settings. So this table here shows the statistics of the data sets that we utilize in our experiments. And the baseline, the comparison baseline varies a lot in different papers. The figure here shows the top 10 widely compared baselines. And we carefully select 7 baselines, which covers different types of recommendation algorithms. Also, there are 2 types of objective functions utilized in those papers. They are pointwise and pairwise objective functions. And around 15% of the papers, they adopt the pointwise objective functions, while around 14% of the papers, they adopt the pairwise loss functions. So in our study, we compare the effectiveness of the both pointwise and pairwise objective functions. And regarding the negative samplings, we find that around 17% of the collected papers consider the unobserved feedback as negative samples when designing the objective functions. While it is not practical to leverage all unobserved feedback, so negative sampling is adopted to balance the efficiency and the effectiveness. In our study, we compare the efficiency of 3 different samplers, uniform low popularity and high popularity. And regarding the data splitting method, we find that around 16% of the papers, they adopt split by ratio. That means they may adopt 18% of the data as a training data and the rest as the test data. While different papers may have different proportion settings. For example, some papers adopt 15% as training, and some papers adopt 16% as a training set. And also some papers divided the user item interaction at the global level, while others at the user level. And some consider step information when they dividing the data, while others do not. Besides, there are also around 13% of the paper adopt leave one out. So in our study, we adopted the split by ratio data splitting method, and we set the proportion to be 18%. We split the user item interaction at the global level by considering the time-step information. And the figure here shows the distribution of the evaluation matrix that are widely used in these paper collections. And for the evaluation matrix, we adopt the top 6 most widely used metrics. So where this precision recall, HR, and MAP measures, or whether a test item is presented in the top-end recommendation list, while MRR and NDCG accounts for the ranking predictions of the test items. And hyperparameter tuning is one of the most important factors for evaluation. And we find that around 14% of the paper directly tune hyperparameters based on the performance on the test site. In fact, an extra validation site should be retained from the training site to help tune the hyperparameters, which is called nested validation. So in our study, we adopt nested validation by returning 10% of the training site as the validation site. And we adopted the Bayesian optimization method as our searching strategy. Here is our experimental results. Due to the time limitation, I don't give the details. Here I summarize some interesting findings from our experiments. So first of all, we find that the recommendation performance does not necessarily improve with denser data set. And secondly, we find that pairwise log loss generally outperforms other types, and uniform samplers, though simple, performs better than the popularity-based samplers. And the baselines with random-aware split by ratio outperforms those with time-aware split by ratio. And besides, the best hyperparameter sightings for one specific metric does not necessarily guarantee optimals with other metrics. As I mentioned, we also released a Python toolkit named as Datasets. So Datasets is different from existing open source libraries, which mainly aims to reproduce various state-of-the-art recommenders. So Datasets is designed with the goal of performing rigorous evaluation in recommendation. So in our library, we consider different data processing strategies, and also we have different types of sampling strategies and the data splitting method, and also different tuners to do the parameter optimization. And to benchmark the evaluation, based on our empirical study, we proposed the standardized procedure in terms of the dataset selections, the data splitting method, and the objective function selections, and the negative samplers, and most importantly, the hyperparameter tuning strategies and the availability of the code and data set. So you can refer to more details, refer to our papers for more details. And also, with the goal of providing a better reference for fair comparison, we report the performance of the state-of-the-art on 6 data sets. So you can refer to our gate for more comprehensive results. So finally, let's conclude our paper. So we aim to benchmark recommendation for reproducible evaluation and fair comparison. We systematically review 85 recommendation papers. We conduct extensive empirical studies to analyze their impacts, and we create benchmarks by proposing standardized procedures and provide the performance of the state-of-the-art. Besides, we also release a Python toolkit, Datasets, from the angle of achieving rigorous evaluation. And for the future work, we plan to consider more deep learning-based baselines and also more diverse recommendation tasks, like the session-aware recommendation. So that's all for this presentation. Thanks for your attention.
Right, Susun, thank you very much. So we have some questions from the audience that I'm going to read for you. So one question is, are you considering some more high-level metrics, such as novelty, personalization as addition in future work?
You mean the metrics? What kind of metrics? Sorry.
Yes, like metrics for novelty, diversity.
Diversity. I think it is very a good suggestion for our paper. But as you know, the experimental results for studying the accuracy part is really time consuming. So this is just a starting point, and after that we will deeper our studies to consider more evaluation metrics and more method and more data set. Yeah. So of course we will. I think it's one of the most interesting directions for our future study. Yeah.
Okay. There's another question that mentions the 12% in time-aware split, and so there's, I guess that's the ratio of part of the split, I guess. And the question is if that might point to information leakage in the model evaluation.
Time-aware split. Slides. So maybe I can share my slides again. I don't know whether which question. Yeah. So here, sorry. I think it should be here. Yeah.
Yeah.
The time aware. Yeah. Here
Exactly.
Here we have the time. Yeah. Because when we do the analysis, we find most of the papers when they adopt a split by ratio, they just adopt the random method. random divide the training and test data. Few of them consider time of error. Yeah, if we don't consider the time of error information, I think there will be some information leakage. Because the real recommendation scenario is to use the history to infer the future. So if you random divide the data, then there will be some future data will be moved into training site, and I think
Okay. And then there are two questions that I will group into one because I think they are related. So it's is your framework like ready for other researchers to use? And a specific question that is the platform friendly to users to include additional data sets and models to analyze results? Like for instance, the question mentions the BetaRec platform that addresses the concern of fair comparison as well. So,
okay, so for first the question, the DesiRec platform, it is very, but I think it is very user friendly, but we will try our best to make it more user friendly because user friendly is endless. So and actually we are keeping updating and maintaining our DesiRec, and the new version will be released soon. So we will make it better and better. We do not stop it now. We will continue doing that. And it is quite flexible. You can consider additional data sets, and you can implement your models. It is very easy to merge your model to our platform. I think this is
Very good, very good. Okay, so thank you, Susan. Thank you for your presentation. And now we're going to move on to the last presentation of the session. It's going to be delivered by Zhenhua Dong from Noah's Ark Lab, Huawei. And this, as I mentioned at the beginning, this is an industry talk. And Zhenhua is going to talk about counterfactual learning and set up new methods for dealing with bias in different aspects of prediction and recommendation. So you can start anytime.
Okay, thank you for the introduction. And good morning, good afternoon, and good evening. This is Zhenhua Dong. Today's topic is about counterfactual learning for recommender system. Here are our collaborators from Huawei and Renmin University. Firstly, I will briefly introduce the counterfactual learning. UDPO defined the ladder of causality with 3 layers. The first layer, association. It learns association with observed data without considering the causality and unobserved data. Most current machine learning applications belong to this layer. Intervention is the second layer. It actively takes action with plans. It can explore new knowledge and causality for making better decisions. Counterfactual is the final layer. It can learn the unobserved world with imagination and counterfactual inference. It has a chance to create new things. Is one possible way to strong AI. Let's see the machine learning community. Southern had a course named Counterfactual Machine Learning. There are mainly 2 topics, modeled world and modeled bias. For modeled world, it can study how to use the partial information data to train full information model. It also studies how to use the offline data to evaluate the online metrics. There are so many bias in the world. The course try to study how to use the counterfactual model to handle the bias. More than half of the course is about the evaluation and the learning problem in recommendation system, information retrieval, and advertisement system, because their bias challenges are significant. Let's see 2 bias challenges. Position bias. Position bias describes the tendency of users to interact with items on top of a list with higher probability, regardless of the item's actual relevance. For example, the document 4 is relevant, but document 4 ranks on the 4th position. The user may can't see it, so the user didn't click it. Another important bias is selection bias. Selection bias occurs when the study population is not representative of target population. Let's see the example. The previous recommendation model doesn't expose the document full. Even document full is relevant, so the user can't click it. How to handle it? Firstly, let's see one interesting question. What kinds of data can be used to learn an unbiased model? Here is my answer. We uniformly expose every item to every user in every context, and each user gives his or her performance, so that we can get the full information. We can train an unbiased model. As we know, we have so many candidates, so it is impossible in real world, but it is possible in counterfactual world. UD4 defined the counterfactual as a probabilistic answer to what would happen if. Today, I will introduce 4 kinds of counterfactual learning approach for recommendation system based on 3 kinds of data: the biased observed data, unbiased observed data, and unobserved data. Let's see our first approach, counterfactual data learning, also named the direct method. The basic idea is we learn the imputation model with observed samples and predict labels of unobserved samples. Let's see the loss function. The first term is a regular term. W is our recommendation model. The second term, L hat means all the samples, including the observed samples and unobserved samples. Here, the label, we use the imputed label from imputation model. There are 2 challenges. The first one, the imputation model is very hard to learn. The second one, high complexity to train all the samples together. How to handle it? We designed the counterfactual learning framework. We use the uniform data to train our imputation model. The uniform data is unbiased, so the imputation model is unbiased. Here, the uniform sample means we expose items to user randomly. We use the imputation model to predict the label of non-displayed samples. And then we train our CTR model with display samples and non-display samples. We efficiently learn with block coordinate descent plus conjugate gradient method to reduce the complexity. Let's see the experiment. With 1% uniform data, our proposed method are better than the baseline method in terms of negative log loss and AUC. As we know, the uniform data is very expensive. So let's see some small uniform data. With small uniform data, our proposed methods are also better. Okay, let's see our second approach, correct biased observed samples. IPS method is one of the most popular methods belong to this approach. Propensity score is defined as the conditional probability of receiving the treatment given pre-treatment covariance. Here's the loss function. For each observed sample, it divided the propensity score. There are 2 challenges for propensity method since the number of candidates is huge in recommendation scenario. The first one, the overlapping assumption is very hard to satisfy because not all the candidates have a chance to be exposed. And the small prediction error for propensity will lead to big model error. How to handle it? We try to use the inference function. This is the definition of inference function. Inference function traces a model's prediction through the learning algorithm and back to its training data, thereby identifying training points most responsible for a given prediction. Here is the formula to compute the inference of sample J in training dataset to the sample I in the validation dataset. Our idea is very simple. We use the uniform data as the validation data. Then we compute each sample's inference, and we use the inference as the weight of the training data. Here is the formula to compute the weight. Phi is the inference function. And with the experiment on 2 public datasets, Yahoo R3 and Code, our proposed method are better than the baseline method. The detailed information can be found in our CGR work. Okay, the third approach combines the first approach and second approach together, double rows method. We have two terms. One term is the IPS method to correct the observed data, and the second term, we use the direct method to train the unobserved samples. As we know, the propensity score is very hard to learn in recommendation scenario. So we just use a hyperparameter to adjust the weight of observed data and non-observed data. Then we use BCD plus CG method to efficient to train the unobserved samples. Okay, let's see our last approach, joint learning with the biased data and the non-biased data together. Firstly, we do a pilot study with our advertisement system. We train two kinds of logic regression model. The first logic regression model trained with only the non-uniform data. The second logic regression model we trained with both non-uniform data and uniform data together. In terms of AUC and ECPM, the combined logic regression model are significantly better than the LR model with only the non-uniform data. The pilot study inspired us to try some advanced method to use the uniform data. So we design a general knowledge distillation framework while uniform data. We propose 4 kinds of knowledge distillation method. The first one, model distillation. It's one kind of classic knowledge distillation. The uniform data as a teacher, it shared a model structure. We learned from the unbiased data. Feature distillation, we learned stable features, stable samples with the uniform data. Label distillation, we try to learn the imputation model with unbiased data and then adjust the biased data. The last one, sample distillation, we jointly learn the biased data and the non-biased data together. The detailed information can be found in our CGI work this year. Okay, this is conclusion. Today, I introduced the 4 kinds of control factor learning method for recommendation system. What's the next? Causality is very important. Current industry recommendation system train complex models with huge number of samples with high dimensional features. It works in some degree, but are we on the best road? For example, I decide to watch a movie tonight just because a friend told me it is a good movie for me. My friend told me it's a causal feature. I hope the future recommendation system can understand the people's decision mechanism and find the most important 1 or 2 causal features. It's very interesting study. Okay, thank you for your listening and thank you for my mentor, Professor John Riddle. I think he will be happy to see my first work in RecSys. Thank you so much.
And I'm sure he will. Thank you, Zhenhua, for your talk. So we have time for a couple of questions. So one question from myself is I mean, I'm very interested in collecting random data. So I mean, the kinds of questions I have is like, how do you do that? Also, when is it enough to, I mean, when do you have enough random data? And what kinds of limitations you probably have to cope with? Like, for instance, I can imagine that the kind of random data, uniform data that you can collect will involve like only a small subset of items and a small subset of users. So, and then you have to generalize that to all items or all users. So, yeah, so the question would be like, how do you collect that and what kinds of limitations you have or how much of it do you need?
Yeah, this is a very interesting question. Yeah, Bowen and I also do some study about how many uniform data are enough. Yeah, as we know, the uniform data is very expensive and for collaboration, for collection. Sorry. So for our experience, we have 1% uniform data, and we can see here. Oh, here. Yeah, we use 1% uniform data. And when we collected 1% uniform data, we lost all the avenue for the 1% uniform data. But we can see here, the eCPM improve nearly 3%. So yeah, I think we need to do the trade-off. It depends on the recommended scenario. It depends on our data. So that is our experience. Yeah.
Okay, thanks. Another question is any of this working in production? If you can answer. is any of this
yeah,
actually
that's
being
part.
applied?
We implement them. Yeah, we implement them. The other method we are working on it. Yeah.
Okay.
It's very hard to persuade the product team to try to use the uniform data, as you know. Yeah, it's very hard. But for research, we can do a lot of things. Yeah.
Okay. Thank you very much, Zhenhua. And I would like to thank all speakers again. And we have to wrap up the session because there's something else coming up. Thank all of you for joining us for this session. And let me tell you to join the next social session, which is going to be the banquet, and in particular because the awards will be announced, like the best paper, best reviewer. So this is going to happen in Gather. Correct me, the students from here, if I'm wrong. So yeah, thanks again. See you around. Thank you very much.
Thank you.